All right, everyone, welcome back. Today we're going to be talking a little bit about um, something called concavity and the second derivative test. So last time we spoke about the first derivative test and how we can use it to find the intervals for which a function is increasing or decreasing. And we also were able to use the first derivative test to actually find out whenever we have a local max or a local min. Today we're going to be talking a little bit more about graph of functions and specifically this thing that I just mentioned called concavity. Now let me quickly define concavity for you. So first of all, let f be differentiable on an open interval I, then the graph of f is concave upwards on I, on the interval I, if the derivative is increasing increasing on the interval and concave downwards if the derivative is decreasing on the interval. Okay, so let me actually draw you a picture so you kind of have an idea of what's going on. So let's say we have a parabola. Let's say it looks like this, right? This parabola from this interval to this interval is concave up. I'm not going to write upwards. I'm just going to say concave up. The reason why it's concave up is because you could see that both of the ends are going up. If you actually take the derivative on this interval, you will see that the derivative is actually positive. Okay, so it is increasing from left to right. Now, if you were to continue, let's say the function continues and it does something like this. Actually, Jesus. Yeah, like that. Kind of wanted to go like this. Anyway, on this interval, which I'll put in blue, from this side, notice that the endpoints are now going down. So this is concave down. Okay. Now when we work with with functions, we can use the so-called second derivative test to actually test for when a function is concave up or concave down. So if somebody just gave you the function like f of x is equal to say f of x equal to some y, you know, if somebody gives you a function, then without graphing it, you could tell precisely on which intervals the function is actually concave up or concave down. So let me actually write that down as well, because that is a theorem, and this is how you test for concavity. So theorem says to let f be a function whose second derivative exist on an open interval I. Number one, if the second derivative of x is positive for all x's on that interval, then the graph of f is concave upward on I. And two, as you probably guessed by now, if the second derivative of f is negative for all x on the interval I, then the graph of f is concave downwards on I. Now this is a test that I like to use a lot because it helps me find on which interval there's definitely going to be a max or a min, because if you notice from here, when the function is concave down, there's a maximum, and when it's concave up, there's a minimum. So if you could determine what the concavity is on the interval, then you definitely know that the maximum occurs on that interval or the minimum occurs on that interval. Okay. Now, let's work on an example. So let's determine let's say open intervals on which the graph of f of x equals to e to the negative x squared over 2 is concave up or down. Okay, so first of all, let's look at the function. We're given the function f of x is equal to e to the negative x squared over 2. Now, if you don't like dealing with negative exponents, you could bring the whole function to the denominator. That is 1 over x squared over 2. Just make the exponent positive. Now, notice a couple of things. From this definition right here, we need f to be differential on an upper interval. We know that the exponential function e is differentiable at all values of its domain, because we rewrote it as 1 over e to the x over 2. We just have to worry about the denominator not being equal to 0. But the denominator is actually never equal to 0 because there's no value that you could plug in for x to make e to the x be equal to 0. Think about it. The graph of e to the x looks like this. There's a horizontal asymptote at 0, so we never actually approach or get to be 0 for e to the x. Now, because f is continuous on the entire real number line, we can proceed with finding the first and second derivatives of f so that we can apply the test. So let's actually do that. Let's take the first derivative of f. I'm going to work with this because it's a bit nicer. Now remember that, in fact, remember that when you take the derivative of e to the x, the derivative of e to the x is e to the x, but by the chain rule, we actually have to worry about what's up here. So what I'm going to do is I'm going to rewrite this. So f of x is equal to e to the minus x squared over 2. And I'm going to say that u is equal to negative x squared over 2. So that means that what I'll have now is f of x is equal to e to the u. And then I'm going to find the derivative of u. The derivative of u, or u prime, is the derivative of negative x squared over 2. Well, by the general power rule, you bring down the 2. There's going to be negative 2x divided by 2. But the 2's cancel out, so this is minus x. Well, if you take the derivative of f, the derivative of f of x is the same. We'll take the derivative of e to the u, but the derivative of e to the u is e to the u times u prime by the chain rule. And now if you bring back the u and the x, what we have is e to the negative x squared over 2 times negative x, which is the same thing as negative x e to the minus x squared over 2. So this is the first derivative. Now, to find the second derivative, to find f double prime of x, well, notice that we have now the product of two different functions, negative x and e to the x. So instead of starting to solve this right away, let me remind you about the product rule. The product rule says the derivative of the first, well, the first times the derivative of the second plus the second times the derivative of the first. Remember that on the product rule, the order doesn't matter, but I write it this way so you remember also the quotient rule. This helps, writing it this way helps you remember the quotient rule. In any case, let's say that f now, for this function that we're trying to find the second derivative of, is negative x. And let's say that g is e to the minus x squared over 2. Well, we know what g prime is. Why do we know what g prime is? Because we did it up here. It's the same thing as u prime. Oh, I'm lying. It's the same thing as f prime. Because notice we're taking the derivative of e to the negative x squared over 2, which is what we began with up here. So the derivative of f of x, which is what we're calling now g down here, is negative x times e to the minus x squared over 2. So we already did this piece of work. I'll actually move this to the side. Negative x squared over 2. So we only have to worry about the derivative of x, of f, which is just minus 1. So we are good to go. So we have now the second derivative of this function is equal to the first times the derivative of the second, so that's minus x times g prime. Well, g prime is minus x e to the minus x squared over 2 times, not times, plus the second times the derivative of the first. Well, the second is e to the minus x squared over 2 times negative 1. That is, again, by the product rule. And now what we can do is we can see what we can factor. We can actually factor e to the minus x squared over 2 from both of them, because notice that it appears here and it appears here. So let me first, before I do all of that, this is minus x e to the minus x squared over 2 minus e to the minus x squared over 2. I just multiplied the minus 1. And now, notice that if I multiply this minus x to the inside of this, I get minus is plus, so this is going to be x squared e to the minus x squared over 2 minus e to the minus x squared over 2, and then I could factor the e to the minus x squared over 2. That's going to be e to the minus x squared over 2 times x squared minus 1 when you factor. So we have that the second derivative is e to the minus x squared over 2 times x squared minus 1. Now, the only way that the second derivative is equal to 0, so to find the intervals for which this is going to be concave up or down, we still have to find critical values, much like we did for the first derivative test. To find those critical values, again, we want to find out when is the second derivative equal to 0. So what we want to find out now is when is the second derivative equal to 0. So that means that I have to solve for e to the minus x squared over 2 times x squared minus 1. I have to solve when is this equal to 0? Well, that's going to be equal to 0 when e to the minus x squared over 2 is equal to 0, or when x squared minus 1 is equal to 0. But we already know from the first step, when we found out that this was continuous everywhere, that this is never equal to 0 because we had that horizontal asymptote. So we only need to worry about this right side. If you add 1 on both sides, you get x squared equals to 1. So we get x is equal to plus or minus 1 when you take the plus or minus square root. So now we know that when x is equal to plus or minus 1, we have that the second derivative is equal to 0, and that's our critical value. But now this piece right here gives us our interval, because this is, we have x equals minus 1, x equals 1. If you draw the real number line, you have minus 1 and 1, right? So we have three intervals where we could test whether the function is concave up or down. One of those intervals is to the left of -1. The other interval is between -1 and 1. And the other interval is to the right of 1. In other words, we're looking at the interval from minus infinity to minus 1, the interval between minus 1 and 1, and the interval between 1 and plus infinity. So much like with the first derivative test, we could make a table, and we could actually determine whether by using the second derivative test, whether the function is concave up or concave down. So let's see. So I have the interval. We're going to pick a test value on that interval. And then we're going to find out by the second derivative test. We have to find out what the sign is, because we have to find out whether the derivative is positive or negative, the second derivative. And finally, we have to make a determination whether it's concave up or down. So you can make a table like this, and then with the three intervals, and let's see what happens. So the first interval that I have is -infinity to -1. Another way of writing that is -infinity x -1. So x has to be less than -1 but bigger than -infinity. The other one is x has to be bigger than -1 but less than 1. And the last one is x has to be bigger than 1 but less than infinity. And now we need to find test values. Well, what is a number that appears on the first interval? Well, what is a number that makes x be less than -1 but bigger than -infinity? Well, if x is equal to -2, that works, because -2 is bigger than -infinity, because you could find values that are less than -2 on this interval. -2 is less than -1, so that works. What is a value between -1 and 1? 0. That's an easy value. And finally, a value between 1 and infinity. I'll just pick 2 again. Okay. Now what we have to do is we have to find out what f double prime of -2 is, f double prime of 0 is, and f double prime of 2 is. We're interested in the signs. So I'm going to do them on the side. I'm going to start with f double prime of -2. Let me remind you what f double prime is. F double prime is this piece right here. So let me just write it up here. So f double prime of x is equal to e to the minus x squared over 2 times x squared minus 1. So what we're doing here is we're going to be plugging in for x. So we have e to the minus 2 squared divided by 2 times -2 squared minus 1. So let's see what we get. We have -2 squared is 4 times a -1, that's -4. -4 um, minus 4 divided by 2 is negative 2. So we have e to the minus 2 here. Times, and this is going to be negative 2 squared. Well, negative 2 squared is 4. 4 minus 1 is 3. Now, don't be fooled by this negative number here. Remember, we have a negative exponent. When we have a negative exponent, we simply write it as 1 over 1 over the expression with the positive exponent, so times 3. So this is simply equal to 3 over e to the 2. Now, this is a positive number. This is bigger than 0. Why do we know that? Well, even though this could be a small number, we know that E, Euler's number, is approximately 2.7. I mean, that's like a very, very bad approximation. It's an irrational number, so this decimal expression goes forever, but we definitely know that this is roughly 2.7, let's say. I think it's actually 2.6, but it doesn't matter. It is a positive number. You have a positive number divided by a positive number, you get a positive number, so this is going to be positive. So we know that this is going to be a number that is bigger than 0. Now, by the test that we had, when we had the second derivative be bigger than 0, then we say that we're concave upwards. So this is concave up. Okay, so we have that this is concave up. How about the second one? Well, for the second one, we have the f double prime of 0 is equal to e to the minus 0 squared over 2 times 0 squared minus 1. Well, 0 squared is 0, 0 times minus 1 is 0, 0 divided by 2 is 0, so we have e to the 0 here. 0 squared is 0, so we have 0 minus 1. E to the 0 is 1, 0 times minus 1 is minus 1, and 1 times minus 1 is minus 1. So this is certainly less than 0, so we say that this is concave down. Finally, for the last one, when f double prime is 2, when you plug in 2 for x, we have the following. We have e to the minus 2 squared over 2 times 2 squared minus 1. So it's going to be, again, e to the minus 2, like before. Then 4 minus 1, again, is 3. So it's going to be the exact same value as before. It's going to be 3 over e to the 2. But we know that this is positive from before. So this is a positive number, which means this is concave up. So the second derivative test tells us when the function is going to be concave up or concave down. I'm going to try to use GeoGebra to plot this. Let's see if my GeoGebra works. It's been a long time since I last used it. Let's see. So let's say f of x. What do I have? I have e to the negative x squared over 2. That was our original function. So we had e to the x squared, and then the whole thing divided by 2. Oh wait, it was minus. So let me see if I can go back. So some minus here. There we go. So now here we can certainly see how the function looks like. So remember what our intervals were. Our intervals were negative 1 and 1. So if you notice here, to the left of minus 1, you're concave up. because notice that this piece is going up. In the middle, we're concave down, because if you just ignore, this is a bit annoying to do, but if you were to just zoom in enough so that you could only see 1 and -1, then notice that it looks like it's going down. But now if you just move all the way to the right, if you look here, this end point is going up. This is actually gonna going to take us into the next piece of this lecture, which is, when do we actually know that we are actually going from going up to going down? Because notice I'm saying that this line to the left of 1, we call it concave down, but then to the right of 1, immediately to the right of 1, we're saying that's concave up. So when do we actually know that this is the case? That is what is called a point of inflection, which I am going to define now. So let's define a point of inflection. In simple terms, because the definition I'm going to write may not be as intuitive, a point of inflection is simply a point where the function changes direction. That's the way that I like to think about it. When you go from concavity being up to concavity being down. The former definition is the following. Let f be a function that is continuous on an open interval, and let C be a point in the interval if the graph of f has a tangent line at this point, and this point will be C comma f of C, then this point is a point of inflection of the graph of f if the concavity of f changes from upward to downward, or downward to upward. At that point. At the point CF of C. So that is what a point of inflection is. In simple terms, if you look at a graph that looks like this, let's say it goes up, down, then back up. Point of inflection for this graph will be a point, and I'm not going to put it on the axis because it doesn't have to be on the axis, but it will be a point such that you could clearly see that the graph went from being concave up to concave down. So here, this piece from here to here, this is concave up. You see that the endpoints are going up. And then from here to here, this is concave down. I like to think about it as follows. Concave up. Looks like this, and it's smiling. Concave down. Looks like this, and is frowning or sad. Okay. Now, I've been talking about the second derivative test, and I just use the second derivative test to solve for inflection. not for inflection, to solve for the concavity of of the function. And I just gave you the punchline. This is something that I'm going to write when I write the official or the formal definition of the second derivative test, but I just mentioned this. Whenever you have concave down, you have a maximum. When you have concave up, you have a minimum. You can see that from this picture. Here you're going to have a maximum, here you're going to have a minimum. So just keep that in mind, because when I write down the second derivative test, is what we'll be working with. So the second derivative test gives us the point of inflection. It gives us the it gives us where the function is concave up or down, and it also tells us where the max or min are when we actually do it. Okay. All right. So let's just do an example with finding points of inflection. But let me give you a theorem, because a theorem is actually what's going to give us the method of finding points of inflection. So if c, f of c, meaning that point, this particular point, c f of c, is a point of inflection, of the graph f, then either f double prime of c is equal to 0, or f double prime of c does not exist. At x equals c. So basically what this is saying is that a point of inflection happens when the second derivative is equal to 0. Okay. So when the second derivative is equal to 0 at a point c, we have a point of inflection. So let's do an example of finding points of inflection. In fact, the first example we ended up finding the point of inflection. I just didn't write it down. So, and you could have multiple points of inflection. It did not need to be just one. Like, for example, as an aside, you could have a function that does something like this. So here you have multiple points of inflection, because you're going from concave down to concave up to concave down again, maybe to concave up again. So you definitely can have more than one point of inflection. Right, so the example is determine the points of inflection and discuss concavity for f of x is equal to x to the fourth minus 4x cubed. This function is continuous at all points in its domain. It's a polynomial function, so we can simply just go ahead and take the derivative without worrying about points where the derivative just does not exist. So the derivative of this function is 4x cubed minus 12x squared. That's the first derivative. The second derivative of this function, if we take the derivative again, well, this is going to be 12x squared minus 24x. So that is the second derivative of the function. Now, once we have found the second derivative, we can set the second derivative equal to 0, and that point of inflection will occur at that point. So we find point of inflection. Okay, so let's see what we have. So if we let f double prime of x equal to 0, that's the same thing as 12x squared minus 24x being equal to 0, because that's what our second derivative is. And then when is that equal to 0? Well, if you put 0 in here, you're going to get 0 because both of these expressions have an x in them, and when you multiply by 0 you get 0. And if you factor, you could take a 12x out from each of them. You have x minus 2, so you have x equal to 2. So the second derivative is 0 when x is equal to 0 or when x is equal to 2. So we have 2 points of inflection here. Okay, we have 2 points of inflection. So that means that we now have intervals for which to test in. So again, if it helps, always write it down like this, because I think it helps. So one of the points of inflections happens at 0, the other one happens at 2. So the intervals that we're working with is the interval to the left of 0, the interval between 0 and 2, and then the interval to the right of 2. That is minus infinity to 0, 0 to 2, and 2 to infinity. So once again, we could make a table to find out the concavity of the function. We already found the points of inflection, so let me actually, well, we found the x values for the points of inflections. So I'm just going to call x values for points of inflection. The reason why I'm saying this is because a point is of the form x and y. We only have the x's here. Okay, so if I do my table, I have the interval, then I have the test point, then I'll have the sign of the second derivative, and then finally my conclusion. And again, the intervals that we're working with are negative infinity to 0, so that means that x is definitely bigger than minus infinity, but it's less than 0. 0 to 2, so x is bigger than 0 but less than 2. And 2 to infinity, so x is bigger than 2 but less than infinity. Well, what could be my test points? Well, what's a value that is less than 0 but bigger than minus infinity? Well, x equals negative 1 is one of those values. You can literally pick any point that's negative. Any point will work. Point between 0 and 2, just pick x equals 1 for simplicity. And a point bigger than 2 but less than infinity, we're going to pick 3. Make our life simple. Now we have to find what is f double prime of minus 1, what is f double prime of 1, and what is f double prime of 3. I'm going to do this on the side. Remember that f double prime of x was equal to 12x. I'm going to use the factor version, so 12x times x minus 2. And we're looking for f double prime at negative 1. So we have minus 12 times minus 1 times minus 1 minus 2. Minus 12 times minus 1 is 12. Minus 1 times minus 2 is minus 3. And I don't care what this is equal to, because it's going to be a negative number. Plus times minus is minus. So this is definitely going to be a negative number, which means that this is concave down. Whoa. Hold on, let me see. Oh, no, my apologies. I put a minus here. It should be a plus. Yeah, I put a minus in front. So this will be minus 12 times minus 3, which is a plus. So this is concave up. Yeah, always double check your work. I just literally put in the minus here when there was supposed to be 1. Right, so f double prime of 1 now is going to be 12 times 1 times 1 minus 2. 12 times 1 is 12. 1 minus 2 is minus 1, so this is going to be a negative number. In fact, it's minus 12. So this one is concave down. And finally, f double prime of 3 we have 12 times 3 and 3 minus 2. These are going to be positive because 12 times 3 is 36, and there's going to be 1, so it's a positive number. So we have concave up again. And that's it. That's what we had to do. So now we know that the following holds. We have points of inflection at 0, 2. We have concave up on this side, concave down on this side, and then concave up again. So I may not have the picture of this, but by understanding how it looks, I can definitely tell you that if I was to plot this, I know that on the endpoints, this is going up like this on both sides, and then in the middle somewhere, it's doing this, right? And somewhere here is switching. Somewhere here is going back up. Okay, so it may not be perfect, but it's definitely doing something like this on the inside. And once you actually get the second derivative test, once we finish talking about it, then you will actually be able to completely plot a function by using the derivative without having to make an extensive table. This is something that was not possible in pre-calculus. So in pre-calculus, depending on who you had, I know in my class if you took me, you will always cover this. In pre-calculus, we talk about polynomial end behavior. For example, if you're given a function that has even degree, if n is even, then we know that the endpoint is either going, we may not know what's happening on the inside. This is not a circle. This is just, we don't know what's going on the inside, but we know that the endpoint on our graph are going up. We have minus x to the n, but again, n is even. Then we know that we have no idea what's going on the inside piece when you get closer and closer, but when you zoom out, we know definitely that this is going down on both directions. And then if you have x to the n and n is odd but positive, then it looks like this. It's going up here and down here. And then when, again, x to the n is odd and n is odd, but this is negative, this is a terrible use of my whiteboard. Terrible use of my whiteboard. But it looks like this. It goes up in one direction, down in the other. But we still cannot say anything about the inside. So we have no idea what's happening on the inside. This, if you go to a pre-calculus class, those students will not have any idea how to plot this without making a very long table. And depending on what your function is, the table actually may be very difficult to compute. Thanks to calculus, not only do we know what the end behavior is, we also know what the local maximum or minimums are. Now, using the test for concavity and inflection points, we know where the function changes direction. So we can precisely tell how the graph is going to look like with our sketch. So that's what's going to lead us now. That's what I'm going to write now about the second derivative test. So let me actually write it, and then we'll do an example. And then that'll be it for this lecture. That's why I kept it as a one long video, because everything is pretty self-contained. In any case, so this is the so-called second derivative test. I use this actually more than the first derivative test, only because if I'm already taking the first derivative, I usually try to find the second derivative, if possible. Sometimes it's not possible. But anyway, let f be a function such that f prime of c, the first derivative, is equal to 0, and the second derivative of f exists on an open interval I, interval actually containing c. And the following two things hold. If the second derivative of c is bigger than 0, then f of c is a relative minimum, and this goes back to what I was saying. Basically, you have, remember that when the second derivative is positive, we have concave up like this, but we have a minimum right here. Okay, and then if f double prime of c is negative, then f of c is a relative maximum. Again, from the test of inflection, when the second derivative is negative, we have concave down, but up here we have a maximum. Finally, if the second derivative of c is equal to 0, then the test fails. So when you plug in c into the second derivative and you get it that it is equal to 0, f may have a relative max or a min, or neither. And when that happens, then you use the first derivative test. Well, so what I was saying, f may have a relative max or mean or neither. And if this happens, this is the one time that the test does fail. And if this happens, then we use the first derivative test. Okay, let's do an example. Maybe I should have split this video. Anyway. So let's find the relative extrema for f of x is equal to negative 3x to the fifth plus 5x cubed. I'm going to explain at the end why the second derivative test is sometimes much more useful than the first. So first of all, notice that this is a continuous function. It's continuous on the entire real number line because it's a polynomial function. The first thing we have to do by the second derivative test is figure out what is the critical number such that the derivative is equal to 0. So we have to find the first derivative. So the first derivative of this is negative 15x to the fourth plus 15x squared. So this is step 1. Step 2, we have to find out when the first derivative is equal to 0. That is, when is negative 15x to the 4 plus 15x squared equal to 0. Notice that both of them have a 15x squared on them, so we could factor that out. So we have 15x squared. Actually, I could even factor the negative 1. If I factor the negative 1, I'm left on the inside with x squared minus 1. And now we could solve. Well, one is negative 15x squared equal to 0, and one is x squared minus 1 equal to 0. If you divide both sides by negative 15, you get x squared is equal to 0, so that means that x is equal to 0. And on this side, if you move the 1 over, you have x squared is equal to 1, so x is equal to plus or minus 1. And you take the square root. So we have 3 critical values. So 3 critical values. X equals negative 1, 0, and 1. Okay, now we have found the critical values. The third step is to find the second derivative. Typically, actually always, I'm doing it this way, but typically once I take the first derivative, I like to simply go away and take the second derivative right away so that I don't have to go back up on my paper. So that's negative 15x to the 4 plus 15x squared. So let me just rewrite what the function was. So f prime of x was negative 15x to the 4 plus 15x squared. So that means that the second derivative is going to be equal to what? It's going to be equal to negative 60 x cubed plus 30x. Yeah. So we have negative 60x cubed plus 30x. I could factor 30x out of both of them. If I factor a negative 30x out of both of them, I'm left with 2x squared minus 1. And now I can apply the second derivative test. How can I apply the second derivative test? Well, I can simply plug in the values for f. So the fourth step is to apply second derivative test. That is, find the sign of f double prime of x for x equals minus 1, 0, and 1, which is the c values that we found from up here. So that simply means that I'm going to do f double prime of minus 1, f double prime of 0, and f double prime of 1. Now, this is different than the previous example. In the previous example, we found test points between, or rather to the left and to the right of each of the critical values. So if I put this on a number line real quick, on the previous example, what we did was we found an interval on this side, we found an interval on this side, then we would have to find an interval on this side and an interval on this side. So that would have been 4 different intervals that we'd have to find test values for. Anyway, so the second derivative at negative 1 is what? Well, we have negative 30 times minus 1 times 2 times minus 1 squared minus 1. That's just what the second derivative is. Negative 30 times minus 1 is 30. Negative 1 squared is just 1. 1 times 2 is 2. 2 minus 1 is 1. So this is just 30. 30 is a positive number. Now, by the second derivative test, which I wrote up here, if the second derivative evaluated at the critical value is positive, then we have a minimum. So now I know that the minimum happens when x is equal to negative 1. So now, remember, this is concave up, which means we have a minimum. Minimum at x equals negative 1. How about for the other one? Well, f double prime of 0 is going to be equal to negative 30 times 0 times 2 times 0 squared minus 1. But 0 times whatever this is going to be 0, so this is going to be equal to 0. Okay? So the test fails. Remember, if the second derivative, when you evaluate it at c, is equal to 0, then the test fails. So we'll have to use the first derivative test here. So the test fails. And finally, for the last one, f double prime of minus 1, actually of 1, I think I did minus 1 already, of 1. We have negative 30 times 1 times 2 times 1 squared minus 1. So that's negative 30 times 2 minus 1. Again, it's just 1, so this is negative 30. Negative 30 is less than 0, so that means that we have, that this is negative. When we have negative, this is concave down, but when we have concave down, we have a maximum. So we have a relative maximum at x equals 1, we have a relative minimum at x equals negative 1, and the test failed when x was equal to 0. So the last thing that we need to worry about for this particular problem is that the test failed here. Because the test failed, we can use the first derivative test. So remember that the first derivative test focused on what happened to the left and to the right side of 0. So if we go back to the first derivative was negative 15x to the 4th plus 15x squared. So let me write it down here. First derivative was negative 15x to the 4th plus, I believe it was 15x squared. Let me just double check. Yeah, plus 15x squared. If I pick a point to the left and right side of 0, and I'm going to pick exactly -1 and 1, that's perfectly fine if I pick them. Then this is what I will get. So f prime of 1 is going to be equal to minus 15 to the 1 to the 4 plus 15 times 1. This is going to be equal to 0. That was a bad point to pick. Let me not pick it because I know, yeah, that's a pretty bad point. That's a critical value, so I know it's going to be equal to 0. Let's pick a half, -1/2. So we have -15 to the 1/2 to the 4th plus 15 to the 1/2 squared minus. So this is going to be equal to -15 times 1/16 plus 15 times 1/4. Just basically multiplying it by itself that many times. So this is going to be -15/16 plus 15/4. And if you combine these, you just have to multiply this one by 4/4. It's going to be -15 plus 60 divided by 16. And this is going to be a positive number. It's going to be 45/16. So it's a positive number. So that means that we are going up from the left side of 0. On the right side of 0, we could pick a half. But notice that we're going to get the exact same solution because there's going to be -15 to the 1/2 to the 4 plus 15 to the 1/2 squared. And there's going to be the same exact solution. It's going to be -15, 1/16 plus 15, 1/4. So again, we're going to get -15/16 plus 15/4. And then this is going to be the same thing as before, 45/16. So to the right side of 0, we are also increasing. And if you remember from last lecture, when you are increasing and then increasing, or decreasing and then decreasing, then that means that you have neither a max nor a min. So there is no max or min at this particular value. So it's neither a relative max nor a relative min. Okay. Now, the reason why I like to use the second derivative test instead of the first derivative test is because it saves you a lot of work, even though you have to take an extra derivative. It saves you a lot of work on the test points, because instead of me having to pick every single test point, if I go to the first derivative and I find out the critical values, and then I go to this, which I did here, and then I go on the second derivative and plug in, then I immediately know whether that critical value is going to be a maximum or a minimum. I don't have to test a point to the left and a point to the right of every single one of them. If I had to test a point to the left and to the right of these 3, I would have to test 6 different points. And, that's annoying. That's really annoying. So this actually becomes much of a time saver. In any case, that is the second derivative test. Second derivative test, again, will help us plot. Now you have tools for finding maximum minimums. We know how to find endpoints and polynomial end behavior. So you definitely have enough tools that if somebody comes up to you in the train and asks you to plot a function, you can safely plot it. Next time, we'll be talking about probably the most difficult part of the course, which is optimization. But I'll leave that for another day. Thank you for your time.